experiments, and then it basically led to the development of quantum mechanics. Okay, and probably in the physics part, physics 1, you already had some idea about the concept of quantum mechanics. Okay, so that's how the entire class, I mean, or the entire the way we will the way we'll proceed in this class. Okay, and yeah, and part 2 we'll discuss about the solid state physics, and part 3 will discuss about the nuclear and particle physics. Okay, so today what we are going to start, we are going to start the first part, that is the statistical mechanics, and we will see that what is the importance of the statistical mechanics, and what is the main objectives, or what kind of property we want to derive in this part. Okay, so I have already shared these slides in the MS Team, so you can just take a look. So the fonts are a bit larger in order to make sure that if you are using a mobile phone, so yeah, it should be not hard to read. Okay. Okay, so now let me change this slide. Okay, not this one. Yeah. Okay. The slide is visible now.
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
So you see, of course, any topic, whatever we are going to discuss here, the first question will ask that what is the fundamental motivation that why we are going to study this topic. Okay, what is the interesting point of these topics? So, for example, you see here, normally when we deal, either
Your
it's a
voice,
class in a class. Sorry.
your voice is breaking, sir.
Is it the case for all of you?
No,
Am
sir.
I
No,
audible?
sir.
No, sir.
Yes,
No,
sir.
sir,
It's
it's
fine.
clear.
Yes, sir.
It's pretty much
Clear,
clear.
No,
it's
sir.
clear,
It's
sir.
clear.
Clear,
Audible.
sir.
It's clear, right? Okay. So maybe for if any one of you, if that is the case, maybe it's you should just try to reconnect. Okay. So yeah, so the motivation behind to study the statistical mechanics, it comes from the fact that in certain aspects of experiment, what we deal or what we try to understand the collective nature of the system rather than studying a single particle. Okay. So for example, here you see the main intention is, or at least what we are trying to do is that overall behavior of a system of particle is related to the properties of the particle themselves. So basically what we are trying to do, we are trying to connect the property of a single particle to the system of the particles, and we try to understand that what is the behavior of the entire system. Because normally you see, if you have a gas and gas is filled in a container, so what you have, for example, in if you see in these images, okay, the cursor is visible. Can you see the cursor?
Yes, sir.
No, sir.
Yes.
Sir.
No,
Okay,
sir.
No, sir.
No,
cursor
sir.
is not visible.
No, sir.
Yes,
No,
sir.
sir.
No, sir.
It's not visual, sir.
Okay, so cursor is not visible. So if you see, there are two figures. So if you see in the left side, so there is a particle, one particle in a blue box. Okay, and in the right side, if you see, there are several particles in a box. Okay. So in a normal situation, what happens that if you are dealing with a gas, or if you are dealing with any system, so basically what you have to consider, you have to consider basically a system of particles where you have large number of particles. So normally it is very you'd encounter only one, let's say only one particle or only one molecules in a gas, rather than what we generally deal with. We deal with a large amount of molecules in a system of gas. Okay. So the fundamental motivation or one of the idea behind the statistical mechanics is that we are not willing to track the motion or trajectory of an individual particle, but what we are trying to do, we are trying to understand that what will happen to the entire group of particles. Okay. So in statistical mechanics, we'll be interested in the entire group of particles rather than studying the individual or the properties of individual particles, how the individual particle is moving, or what is the history of individual particles. Okay. So what we'll do, we will collectively study the properties of large number of particles, and we will not going to study the individual or detail of individual of particles. Okay. The question is, in what circumstances we are interested in single particles, and in what circumstances we are interested in a large number of particles. Of course, if you are performing, let's say, an experiment on a gas, so what you have a large amount of particles, so it is better to know how a group of particles will behave rather than knowing how individually particle will behave. Okay. So from this slide, the takeaway message is, in statistical mechanics, doesn't matter whether we are going to study the quantum system or the classical system. We are interested only in the properties of a group of particles, not in a single particle. Okay. So normally these systems are divided into two classes. So one class of system is called as classical system, and the example of classical system is basically molecules in a gas. And another set of systems, what we call them as a quantum mechanical system or quantum systems. And in these quantum system, what we deal with free electrons or photons, for example. So free electrons in a metal or photons in a cavity. Okay. So the question is, what is the difference between a classical system and a quantum mechanical system? So anyone can try to explain what is the difference between these two systems?
The classical system will deal with the molecule, with the matter which will have particle nature, and quantum mechanics will deal with the matter which will have wave nature.
So this
Plus
is one way to
the
distinguish.
size matter.
Yes.
Plus the size matters, sir, because we can neglect that relativistic approach in classical system, but can't in quantum mechanics system.
Very good. Yes. Another explanation. Anyone else?
Sir, sir,
Yeah, please.
sir, in classical system, we can find a particle, but in quantum, we can find a particle within a range.
Okay. So have you heard about the concept of distinguishable and non-distinguishable or indistinguishable particles?
No, sir. Can you explain?
No. Okay. Okay. Yeah. Sure. We will discuss in that. Yeah. So, what happens as the name itself indicates that in the set of distinguishable particles is the collection of particles where you can track individual particles or identify individual particles, right? Where if you have a set of or non-distinguishable or indistinguishable particles, so in these cases it is impossible to distinguish that which particle is which particle. So for example, if you have a hydrogen molecule, and in hydrogen molecules, what we have two hydrogen atoms, right? So these two hydrogen atoms, they share the electrons, and now when inside this hydrogen molecule, it is very hard to distinguish which electron belongs to which atom. So in this case, you say that the electron is basically are behaving as a indistinguishable particle. While, for example, in classical physics, we encounter several systems where you can monitor individual particles and even you can classify that, okay, this particle belongs to that system or this particle belongs to that system if you are coming together with a different set of systems. Okay. So the simple idea is that if you have a particle, if you have a system where you can identify that these particles they come from that, means if they carry their identities, you can call them as a distinguishable particles. But if they lose their identity and it is very hard to identify that which particle is coming from where or which particle belongs to which system, we call them as a indistinguishable particles. Okay. So in the classical systems, normally what we, for example, here, obviously the name indicates this classical system. What we deal with the molecule levels, and in the quantum systems, what we deal with photons, or we deal with the electrons. Okay. Now we'll see in these two cases. So either it is a classical system of classical, either it's a classical system or it's a quantum mechanical system. So we have will apply different kind of statistics. Okay. So for all those particles where we can distinguish them, or where the classical physics more or less applicable, normally we deal with the Maxwell-Boltzmann distribution, or Maxwell-Boltzmann statistics, or mechanics sometimes is also called as, and distribution is also the word which can be used. Okay. So you see the first one here in this slide, the Maxwell-Boltzmann distribution, it is applicable on those particles where the classical physics law is also valid, and on top of that, for example, it is normally it is used to study the molecules of a gas. Okay. And in the quantum mechanics, or in the quantum mechanical system, what we use Fermi-Dirac distribution, or Fermi-Dirac statistics, and Bose-Einstein statistics, depending upon the fact that whether we deal with a fermion or we deal with a boson. Okay. Have you heard about the concept of fermions and bosons?
Yes, the
No, sir.
fundamental particles.
No.
Yes, ma'am.
Okay.
Yes, sir.
No, sir.
Okay, so in the next class, we'll also discuss about the so this classification. So broadly, what happens that normally on the basis of a spin. So if you read about the classification of fundamental particles, so on the basis of a spin, the entire set of particles, entire set of fundamental particles are categorized into two parts. The first one we call it as a fermions, and the second one is we call it as bosons. Okay. So we'll see in detail in the next class how this classification is being done. And one of the fundamental property or fundamental rule, if you remember from your previous studies, is Pauli exclusion principles, right? Have you heard about it? Probably in your 12th class.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So these fermions, they normally obey these Pauli exclusion principle. Okay, and in the bosons, they are not, it's not, they don't obey these Pauli exclusion principles. Okay, so they are not obliged to obey the Pauli exclusion principle. So can anyone tell me what is the Pauli exclusion principle? Do you remember?
Sir, in an orbital, there will be two electrons with opposite spin only.
Okay. Anyone else can try that?
That is a maximum
No two
of two
electrons
electrons
can
can
have.
reside in an orbital with opposite spin.
With a positive spin. Okay.
Quantum number are not
Anyone
same.
else?
Quantum number are not same for the two electron.
Yes. Yeah. Anyone else? So basically, all these statements are true, and they are indicating the same principle. Okay. So once you read this Pauli exclusion principle, you will find that there are different way to say the same principle. Okay. So normally it is saying that no two electron can occupy the same quantum state in a given system. Okay. So it means if you have let's say a set of electrons, so in a particular atom, so what happens that these electrons, if they are fermions, so these electrons, of course electrons are fermions, So electrons, they do not occupy the same quantum states in the system. So if you see the energy states of the electrons, so what happens that there are different energy states for each electron in a particular atom. Okay, and, and if you see the in terms of quantum numbers, so the quantum numbers will not be the same for any electrons in a particular atom. Okay, so these particles where Pauli exclusion principle is applicable for them, they follow normally this Fermi-Dirac distribution, and those particles, basically the bosons, they follow this Bose-Einstein distribution. Okay, so why we are interested in these? Of course, the way these particles will behave, it depends upon their fundamental properties as well. Okay, so in order to understand the molecules of a gas, or let's say a gas, we'll see or will apply the Maxwell-Boltzmann distribution. And if you are dealing with fermions, you apply the Fermi-Dirac distribution. If you are dealing with bosons, you apply Bose-Einstein distribution. Okay, so first thing you have to distinguish when you are dealing with a particle, say whether it is a classical particles like a molecules, or it is a fermions, or it is a bosons. Okay, so it means if you have a system of particles, so first you have to distinguish what kind of what is the nature of your particles are in that container, or in that box. Okay, so it should be clear in your mind that if you're dealing with molecules, let's say, then you apply the Maxwell-Boltzmann distribution. If you're dealing with fermions like electrons and so on, you have to apply Fermi-Dirac distribution. If you're dealing with photons, if you're dealing with bosons, you have to apply the Bose-Einstein distribution. Okay, so this has to be clear in your mind that in what circumstances which kind of statistics we are going to, or which concept of statistics we are going to apply. Okay, so the first one, Maxwell-Boltzmann distribution, is applicable to the classical systems where we deal with molecules, and the second and third one, Fermi-Dirac distribution or Bose-Einstein distribution, they are applicable to quantum systems. And within quantum, if the particle is fermions, you apply the Fermi-Dirac statistics, and if your particle is bosons, you apply Bose-Einstein distribution. Okay, so the first one is so-called, sometimes it is also referred as classical statistics, and collectively second and third, they are known as the quantum statistics. Is that clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. So okay, so now we are going to study these three kind of statistics. So what is the main idea, or what is the fundamental motivation, or what we are going to derive in while studying these three statistics, is the fact that, let's say that if the total amount of energy E is distributed among the n number of system of particles, and we are talking about thermal equilibrium at absolute temperature. Okay, absolute temperature T. Okay, so have you heard about the concept of absolute zero or 0 Kelvin temperature?
Yes,
What
Yes,
happens
sir.
at the
Yes,
0
sir.
Kelvin temperature?
Yes, sir.
Yes, sir.
Generally the movement should stop, but it doesn't stop because of that uncertainty principle.
Yeah, so what happens at 0 K? So if you have a 0 Kelvin, I'm not talking about 0 degrees Celsius, we are talking about 0 Kelvin. So it means we're talking about minus 273 degrees Celsius. Okay, so what happens at that point? So if you have let's say if you have a system of particles, and you decrease the temperature of the system of particles, and you can, if you can attain this 0 K, what will happen to your system of particles?
It will be
Motion
So
of
which
attached.
particles
property will
gets
be
stopped.
affected? Which property of the system will be affected?
Motion gets affected.
Kinetic
Exactly.
energy.
The kinetic energy of your particles, individual particles, or or motion of individual particle will be largely affected. Okay.
Yes, sir.
So it means at in principle at 0 Kelvin temperature, what should happen, that you should not have any kind of motion in your particle. Okay. So what is the minimum temperature which has been achieved in laboratory? Do you have any idea about that? Is it 0? Whether 0 Kelvin has been
30
achieved?
Kelvin,
No,
sir.
no, no,
30 to 40.
0.01, I think.
Little more than 0.
So
30.
any idea up to what extent the
Helium has been cooled up to 0.001, I think. I'm not.
-193 degrees Celsius.
So
heard
yeah,
about
you
that,
just
but
yeah. So the homework of today would be to just read about what is the minimum temperature which has been achieved so far. Okay, so just look for it. You don't have to submit anything to me, but we'll continue that discussion in the next session. So just look for it, that what is the minimum temperature which has been achieved for any system of particles in laboratory. Whether it is whether we have really achieved 0, or it is still very far from 0. So whether 10 to power, for example, 10 to power minus 9 up to 10 to power minus 9 Kelvin has been achieved, or even more than that. So just look for it. Okay, that would be really interesting to see that up to what extent minimum temperature has been achieved. Okay. Actually, people received. I mean, some of the scientists who are working in this low temperature physics, they have received Nobel Prize when they managed to study the properties of particles at a very low temperature. Okay. So now what we are interested in, okay, coming to our topic. So we are interested in that. So for example, let's say that the total amount of energy is E, and this energy is distributed among the n number of particles which is present in our system. Okay. Now what happens, that there are in this system of particles, or in this system, what can happen, that different energy states, it is also possible that this system will have different energy states, like what we see in atoms. Okay. So let's say there are n number of energy states. So for example, E1, E2, E3, and En. Okay. So now we are interested in to determine that how many particles from this n number of particles, they have energy, or they carry the energy of E1, or this, or in other words, they have energy E1, and how many of these particles out of n number of particles they have energy E2, and how many of particles they have energy E3, and so on. Okay. So that would be the main task we will derive in the next class, and we will see that how this property of the particle will tell us about the collective nature of our entire set of particles. Okay. So I again repeat, what is the objective? So let's say that the total amount of energy E is distributed among n number of particles. Now within this system, what we are saying, that there are different sub energy levels, or sub energy, or let's say this energy E is basically is coming in a different set of energy. So E1, E2, E3, and so on. Now what we want to know, out of n number of particles, how many particles they have the energy E1, and out of n number of particles, how many particles they have the energy E2, and how many particles they have energy E3, and so on. Okay. So that is the main objective we will derive, and we will see that how it will lead to the formula which Maxwell and Boltzmann they independently derived. And with the help of these particles, or with the help of this formula, we'll try to understand the behavior of set of or behavior of gas. Okay. So let's create a hypothetical situation. So what we have? So let's say that we have a container, and in container we have let's say n number of particles. Okay. So if you try to understand that how these n number of particles in this container are moving, so let's stick to one properties of this particle, and this property is velocity of the individual particles. Okay. So whether all the particles in this container will have the same velocity, or the different particles may have, or means the particles will have different velocities. So what
Excuse
is
me,
your
sir.
perspective? Yes, please.
Sir, the same slide is visible. So have you changed the
Sorry.
slide? Sir,
No,
have
no,
you
no, no.
changed the slide?
Yeah, no. Slide is the same. Okay. So I'm just trying to initiate the
Sorry.
discussion for the next class. Okay.
Different
So
velocity.
yeah. So what I'm saying here is that so for example, let me just go back to this one. So now you see it's one of the previous slides. So the topic of this slide is role of statistical mechanics. Okay. So it must be visible to all of you now. So if you see on the right side, so right side, if you see on the right side, so what happens that you see there are several particles in this container. Okay. So now we stick to one property of these particles, and we call this property the velocity. Okay. So now we try to understand that how the velocity of individual particles uh, is whether it is a constant, whether all the particles have a constant velocity or different particles may have different velocity. So what do you think?
It should be different, I
It's a
guess.
different velocity, sir.
Different
Yes.
velocity.
Yes.
So
So
different
now,
velocity.
yes, that's very good. So all the particles, they will have different velocities. Okay. So what we can do,
Excuse me,
we
sir.
can plot a velocity. Yes, please. Anyone?
Sir, why do we have different energy levels within a set of molecules?
Can you repeat the question? I could not hear you properly.
Sir, why are there different energy levels for molecules within a container? Why do they all not have same amount of
No, I'm
energy?
not talking about the energy levels. I'm talking about the velocity here. So energy level, what we discussed here, we were trying to we are trying to study that the what is the different energy of a for example, here in these cases, for example, if the total amount of energy is distributed among the n number of system or n number of particles, what we are trying, what I wanted to show here, that because if you remember from the study of atoms, so let's say the if we talk about the electrons, so these electrons, depending upon in which depending upon their location, in the sense that whether they are in 1s orbital or 1p or so on, so their energy states will be different, right? So electron, the different electrons of a particular atom will have different energy states. So that's what I mean here. So because if you have a complex atom, so the electrons will be organized in a certain way, and each electrons will have different energy states. Okay, so that's what I mean here. So what we will try to do while studying the statistical mechanics, either the classical mechanics or quantum classical statistical mechanics or quantum statistical mechanics, what we will try to understand that how many of particles they are present, or they are having this one energy states, that is E1, and how many particles they are present in, or they have E2 energy states, and so on. Okay, so that is the main objective, or that's what the message I wanted to convey. Okay, now here what we are trying to do, here we are trying to stick ourselves particularly for the classical statistical mechanics, we are trying to stick with the fact that the velocity of individual particles are different. Okay, so here what we are saying that if we have a system of particles, let's say n number of particles are contained in a container. So if you track the individual velocity of a particle, so these particles basically they will have different velocities, right? Now, if you monitor the velocity, so you may find that this velocity is linked with the temperature of your system. So the moment you increase the temperature of your system, you see the velocity of individual particle will increase. Once you decrease the temperature of your system, the velocity associated with individual particles will also decrease. That's what happened when we talk about the concept of zero temperature. So at zero temperature, the movement or the motion of individual particles is basically is almost zero. So they are not moving in the system. Okay. How you can measure it? So you can, the pressure, the gas pressure is coming from the fact that individual particle of the gas is hitting the wall, and they are coming back and again hitting the wall. Basically, they are transferring the momentum into the wall. Okay. And if you cool down system up to absolute zero temperature, so what happens that at absolute zero temperature, there is no motion in the particle, so the particle is not moving. So you see that this gas pressure is almost zero, or if the particle is not moving, you will not see any kind of pressure on the container. Okay. So what we'll do, we'll see how this velocity is distributed in terms of individual particles. So let's say if you make a table, so if you prepare a table, you have n number of particles. You see that how many particles. So for example, if you on the y-axis, I don't have that plot here, but what you can immediately think of, if you can plot the number of particles, so let's say n on y-axis and velocity of your particles v on x-axis, so you will see a kind of distribution that how the velocity of several particles in this container, they are distributed. Okay. And that is the topic of our next class. Okay. So we'll see that once you monitor the velocity of a large number of particles, so these velocities you will see, so a large number of atoms or large number of molecules, let's say in these cases, they will have a range of velocity, and this will basically tell us about the most probable velocity or most probable speed of individual molecules in our container, right? But some of the particles, you will find that some of the particles they have very high speed and very high velocity, means they are moving very fast. And some of the atoms, some of the particles, it is better to say particles rather than molecules or atoms at this point. So some of the particles, they have very high energy. Some of the particles in the system, they have very low velocity. Okay. And large number of particles in the system, they will have a certain amount of velocity. That will be the average velocity of our system, average velocity of individual total particles of our system. Okay. So we'll see in the next class how the Maxwell and Boltzmann, they derive by using the velocity, they derive their formula by using the concept of velocity associated with individual particles. Okay. So we'll also see what will happen, how this plot of number of particles versus velocity changes once we decrease the temperature of the system and once we increase the temperature of our system. Okay. Is that clear?
Yes, sir.
Yes.
Yes.
Okay.
Yes,
Now,
sir.
Yes, sir.
so now what you can think of, the key point here is that whenever you encounter the temperature or whenever you encounter the velocity, okay, so you see immediately, for example, if I say there is a system and the temperature of a system is, let's say 200, let's say 200 degrees Celsius. Okay. And we have another system where the temperature of the system is 500 Celsius. Okay. Now, so you have the thing which should immediately emerge in your mind, that the higher the temperature is, the velocity of individual particles present in the system would be higher. Okay. So it means the velocity of a system and the temperature is basically, they're linked. Okay. So that's the takeaway message for today's class. And tomorrow, not tomorrow actually, so on Monday, so next class is at Monday at 8 a.m. right? Or is it 9 a.m.?
9
Anyway, 9, sorry. So
9
anyway, I will send a
sir.
message.
9,
Yes.
sir.
Yeah. So on Monday at 9, we'll start our discussion and we'll deal with this distribution profile of velocity. If we have a container and you put n, or we assume that there is n number of particles, we'll see that how the velocity of a large number of particles and some of the particles will change and will be affected. once we decrease or increase the temperature. Okay.
Okay, sir.
Okay.
Okay, sir.
Okay, guys. So I'm just going to put this slide in the MS Team. So if you want, just for your reference, so you'll see that.
It's compulsory.
Sorry.
We have to make notes.
No compulsory. The thing is that you understand what we are discussing. That's it from my side. I don't need notes. Okay.
Okay, sir.
Up,
Thank you, sir.
you just yes. So the thing is that I will share the slides, and it is better if you prepare your own notes, and it will be for yourself. You don't need to share it, or you don't need to send me. So it will be better if you just prepare a note for yourself. Okay. So
Thank you,
you
sir.
write down that what we have
Okay,
discussed
sir.
in the
Thank
class.
you, sir.
Okay. So
And
that's
we have to follow that same book which we had followed for physics 1.
yes. So in that book, so the chapter is called as just let me see what is the exact name of this chapter. So the book is Arthur Weiser, and you see the
Chapter 9.
Chapter 9. Yes, exactly. Chapter 9 is the statistical mechanics, and then the 10 would be, I think, solid state, right? From the 10 onwards, solid state will start. But chapter 9 is basically, if you can follow chapter 9, that will be the basic content of our part 1. Okay.
Sir,
Yes, sir.
Yeah, please.
sir, E1 and E2 are the quantized energy state.
Yeah, so what happens that the energy of means if you see, if you talk about the individual energy of individual electrons, you see these energies are quantized. Okay. So electrons cannot have a continuous range of energy. They can only have a certain amount of energy. This is the concept of quantized energy, right? And these concepts were proposed in order to explain several phenomena what we observe. Okay, particularly the emission and absorption feature, emission and absorption spectrum. So these concepts were proposed, and now, of course, this is the main fundamental basis of quantum mechanics. Okay. So initially, the classical mechanics was really doing well, but suddenly some experiments was performed, and they found some interesting phenomena. For example, the spectrum, black body radiation, and photoelectric effect. So there were several phenomena at the time in 1900s, near 1900s, or just before the 1900s. So these phenomena were, it was almost impossible to explain these phenomena by using the classical mechanics or classical physics. Okay, so this new branch of physics emerged that is called as quantum mechanics, and the fundamental principle is that the energy is basically is quantized. It's not like a continuous form of energy. So electrons, they will have quantized energy. So they can only have certain amount of energy, and these energies are quantized. Okay.
Okay, sir.
Okay.
Okay, sir.
Okay, sir.
Okay, guys. So then let's meet on Monday, and then we continue our discussion. Okay.
Yes, sir.
Okay, sir.
Sure.
Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir.
Okay, guys. Yeah. Bye bye.
Thank you,
Take care.
sir.
See you on Monday.
Thank you, sir.
Thank you, sir.